Afternoon, everybody. I can imagine yeah, it's one of the last things I think of the conference. So I hope you're all energized. Yay! um, yeah. So hi everyone. I'm Daan, Daan van Ness. I'm a product owner of the team short-term forecasting at Alliander. It's not on this slide actually. I see now, but on the next slide I will say something about Alliander. And I will speak about net congestion forecasting today. So yeah. So yeah, is it working? Yeah. So Alliander, Leander, they're both used. Alliander is you could say the group, and Leander is the distribution or the operator. And we are distributing energy. So in the Netherlands, that means we're not producing or storing any energy. We're really the distribution system operator. So we take energy from the national, from the transportation grid, from TenneT, but also from solar farms and from homes, clean energy providers, and we distribute that to offices, factories, data centers, electric vehicles, yeah, the whole society, you could say. And the blue area here is the Leander or Alliander grid area. So it's about 1/3 of the Netherlands. So yeah, millions of connections. And we also have why do you do system operations? So system operations is the SO of the DSO. Well, you can see I have a couple of news articles here. They're Dutch, but I'll translate them. So you can see over the last year, the grid operator is really in the news. You can see there were queues for the grid getting longer and longer. Even schools are affected. And yeah, the grid operators are saying it's going to take at least 10 more years to resolve grid to net congestion and waiting queues. They're calling for charging points to be switched off at night. Like solar and PV installations are failing at some moments during the day. And yeah, it's been made easier for grid operators to temporarily reduce or switch off solar and wind parks at busy moments. Yeah, and the companies are solving this with each other. So I think these challenges now at the end of the conference are quite clear to everybody. I think lots of talks have highlighted these problems, so it keeps coming back. But that's good. It's clear we have what the problem is, I think. So what it results in the Netherlands, this map has also been shown, it's quite full. So here is for consumption on the right, it's for generation. It's for like larger customers, so not households. Households obviously can still, well, not all of them, but most of them can. The new still like get a connection, but yeah, the whole of the Dutch grid is quite full, and so you could say there are two solutions for this problem. You could just physically increase the grid capacity, of course. You can just put more cables in the ground, more transformers, bigger transformers, but this takes years, not only because of the resources, the materials, the personnel to do it, but also it takes permitting takes years, so yeah, this will be a long-term solution. Of course, it has to be done, but it's not the only thing that you can do. We have to also create smart solutions to manage energy flows in a smart and flexible way. Because yeah, you've also heard it. I feel like I'm repeating everybody at the conference here because everybody has put this in their introductions, but then at least it's quite clear. The grid capacity is determined by the peak. So there is a peak at the day. It's either consumption or generation. Oftentimes in the Netherlands, actually the generation is the problem, not so much the usage. But here you see an example of a usage consumption peak, where at night there is a consumption peak, and that's actually the problem on the grid. And you can see all this purple is still room on the grid, so there's transportation room for energy. So if you can shift this peak, or yeah, you can make more of the existing hardware that's in the ground. So how is it done? At Leander, the department system operations developed a system called GAS, we call it, Grid as a Service. And it can consist of many components because a lot has to be done to automatically manage congestion on the grid. And you can also see there is a state estimator here, which we use. The power grid model is used there a lot, so there was already a talk about that. You could have, maybe if you attended that, then this looks familiar. And you can also see there is a short-term forecaster in there, which is the forecaster module that I'll be focusing on today. So looking at this system from the lens of forecasting and net congestion, you see, what do you need? Well, of course, first you need to create a forecast. So what is a forecast? It's given at a point of time what's going to happen at this specific location in the grid for the next few days. And below is the forecast, and you can see it's a probabilistic forecast, so it doesn't only generate the expected value, but some bands of, let's say, 90% or 95% chance of that the realized load will fall in this range. And this is done for, like I said, one specific point in the grid. So we do this for many points in the grid to assess what the situation will be of the whole grid in the upcoming few days. And then, of course, the next thing you want to know is what are the limits everywhere in the grid. So you need to know what is all the hardware that's installed and what are their physical limits. And once you have that, you can superimpose the limits on the forecast and say these are the problems or the net congestion that's going to occur in the next few days. Yeah, I'm simplifying things a bit because yeah, to get here, yeah, you need more steps, but at least that's the core of it. And then you know if you need to take an action or not as a grid operator. So then you need to know what is our solution space, what is all our customers that are connected to it that we might have a flexible solution with. And you need to know the topology of the grid, which can change, of course. So this is also one of the components, key components in the system. And once you know that, it's important that you know how much time do we still have to solve the problem. So let's look at this timeline. Let's say if you would have detected an overload at this moment in time for 2 days ahead, let's say, then there's still some time to activate a particular product, which in this case is a bilateral agreement with a wind or a solar park that you can agree to call them and say the capacity is reduced for tomorrow between this and that hour. Yeah, that's a form of contract that now exists. If you're a bit later with detecting that or solving it, you can go to the redispatch market, or you can go to some forced markets, or even if it's really close in time, there are some forced or like some emergency measures that can be taken to make sure the grid stays safe. So you would like to see this coming early in time. And yeah, in total there are lots of energy markets. So these are the flexible products we have today, but this can change, of course, over time. So the action space will change. But yeah, what I wanted to focus on today is a bit the forecasting side of this. So it's I want to start this with a quote where it says, "The goal of forecasting is not to predict the future," maybe controversial, but but to tell you what you need to know to make meaningful action in the present. So it's not about actually precisely knowing what's going to happen in the future, but you just need to know something so you can take an action now. So with that quote as a starter, some background about forecasting. This is what the load on the grid used to look like for a long time. It was very consumption dominated. You can already see some patterns. You can see the weekends and the weekdays. And every day of the week there is like this double peak with a morning and an afternoon where people use a lot of electricity. And it's quite regular. You can already see, you could almost by hand draw this line for into the future. But then, of course, there is now a lot of renewables on the grid. And the first source is solar, which causes problems. You can see on the grid it causes actually, it's not consumption. In this case, consumption is the positive part, and generation here it goes into the negative side. So you even can get negative loads on the grid. which you see are there on some days, but not every day, of course, because the sun doesn't always shine. And it's not every day, it's not as deep, the peak, because sometimes there's more sun than the other days. So it's much more erratic already. And here's an example of a wind-dominated load profile, where you see that it can sometimes the wind can be tough for a couple of days, then it can be lower. So it's a quite different profile from the solar dominated profile. It's not regular, it's not every day, it's much more changes over time. And usually you have a mix of these things on the grid, of course. So let's see, there's two approaches you could take to forecasting. One thing you could do is, if you know everywhere in the grid what the installed PV capacity is, what the installed wind capacity is, you know how everything is connected over time, and you know what the weather is going to be in the next few days, you could just calculate basically what the yield is going to be. But you would need to know a lot of information, especially in a huge grid area. And these things change over time, of course, because the installations change and a lot of things change. So it is theoretically possible, but it's going to be also quite tough to achieve. So what, an alternative way is to learn it from data, to learn the relationship between weather and power on the grid. And by that, the model doesn't need to be fed with a lot of information about PV installations or wind installations, but it just infers if the sun is going to shine this bright on that location, that means that that much power is going to be on the grid. So that's the approach that we take. It's a pragmatic approach using openSTEF. So it stands for short-term energy forecasting, where we already saw this plot. You have a historic load and you want to know what happens 2 days into the future. So what is openSTEF? It's a complete software stack, so it's not just a Python module with a model, but it has all these different steps in it. It includes data validation, feature engineering, training of a model, forecasting, all these data science steps, machine learning steps that you need to take. And we just had the workshop, so some of you may have attended those, where you could see that it's quite easy to actually train a model, just a few lines of code where you feed in some information, which I'll go talk briefly about. So the most important thing is the load. So you have for one specific location on the grid, you know what the load was at all these moments in time. And then the most important things that you add are you need to fetch your own weather data from some source that you have, or maybe some open source or your own source. And actually now it only gives one variable, but you give it a lot of variables like radiation, temperature, all these things that are important. And you also pass it market price. That's also something that has an impact on the situation on the grid. And what if you then also, the weather variables are very useful for estimating the generation components. And for usage, what we use is the typical profiles. So we get them from the Dutch organization, or I don't know if it's Dutch actually, but MFF BAS. They publish these profiles for schools, houses, factories, all these different types of users throughout the whole year, what their typical usage will be. And so those are like 12 or 20 something different types of profiles that you can add. And openSTEF then calculates from the input that you pass it some additional features that we know are important for power on the grid. So for instance, of course, to know what the load on the grid is going to be today or tomorrow, it's important to know what it was yesterday or the last week. So those are lagged load features. We derive some weather features, so compute, for instance, global tilted irradiance, that's like how the sun actually hits the earth, and how it would hit a solar panel. Add some calendar information, so add a lot of, enrich basically your input data that you would pass to it, and it would create a forecast. So from here on out, it sounds great, but there are some challenges to a machine learning approach, which is that it completely depends on data, and the data that you pass to it, and the quality of the data and how representative the data is that you pass determines how good the forecast will be. And the issue that we see, of course, is that the situation in the world is changing a lot. So you can see here the amount of installed solar energy in all of the different Alliander sub-areas in from 2011 to now, so like 10 years, a bit more. And you can see it's really exploding. Wind a bit less, but still growing. And for consumption, you see the same thing. So on the bottom left, you can see the amount of the charging points for electric vehicles. And on the right, you can see the amount of heat pumps. So yeah, the world is changing both in the consumption and in the generation side, which means that if you would train your model on data from last year, how the relationship between radiation and load on the grid last year was quite different from now. Because now, if the sun shines, there will be a lot more electricity on the grid than last year. So an alternative approach is that and that's actually the approach that we take, is we train only on a short horizon. So we train on the past few months of data only to make sure that you train on very recent situation on the grid. But then, of course, if you train on a period that's smaller than 1 year, yeah, it depends on which season you're in. So here you can see radiation, solar radiation from the weather provider. And you can see that, of course, in January, in the winter, the solar radiation is not so large, and then it just keeps increasing as we go into the spring and summer. So if you would train your model on this data, yeah, what is it going to do in the days and months that come after that? Can it accurately predict the first few really sunny days in spring when you suddenly hit a lot of solar hits the grid? So you can forecast with a lot of different models, ranging from complexity. You can start with linear regression. Maybe that's something that everybody will recognize. And you can go into more and more complex models, with deep learning being one of the most complex forms, and decision trees are somewhere in the middle. The thing is, the more complex you get, the more parameters will be in the model, and the more data you need to fit it well. And with the approach that we take with small data sets, we generally tend to use linear regression and decision trees at the moment in openSTEF. But these models have very different properties. So let's see. Let's look at that situation from before, where we train on January and then try to predict February. What you see on the x-axis here is radiation, so more and more sun, and then more and more load on the grid. And in the training set, the radiation only went up to here because it was winter. And then in our prediction set, where we want to make predictions, we have more sun. But how will the model accurately capture that? So one of the properties of decision tree-based models is that they will, if you don't do anything special with them, they just look up the same situation from the training set that's most like today. So they will say tomorrow is going to be like the most sunny day from January. But the most sunny day in January is not sunny enough to forecast what's going to happen in the next month. So yeah, in technical terms, it doesn't extrapolate. It just keeps on predicting the same value, unless you retrain, of course, very often. Then a linear model has the nice assumption that it extrapolates linearly. So it just says, well, whatever I learned in January, even though the sun was not so high yet, and there was not so much sun, I can just assume that if there will be more sun, I will just assume linearly that there will be more power on the grid. Which is nice, but again, also has a downside where you see it will just keep on doing that, even though at some point maybe there's not going to be more, the solar capacity is at the max, the solar panels can generate more at some point, or the wind, if this would be wind, the mills cannot spin faster, so there will be some limit. So they both have some downsides and upsides, of course. But here's an example on the different two models on a location on our grid, where I wanted to highlight some things. So for the decision tree-based model, we use XGBoost. Maybe it's a model that people will recognize. It's a very powerful and often used model, which can do quite a lot. But there are some downsides to it as well. For instance, here. And yeah, you can see the linear model on the bottom, where the red line is the actual data and blue is the forecast. Forecasts the peaks quite nicely. So you can see these peaks were not there at the beginning of February, but then at the beginning of March this year, there was suddenly a lot of sun, and the linear model was able to forecast that. So even though it's a very simple model, it's one of the simplest models out there, it was very good at what we needed it to do. Where as you see the XGBoost model, it didn't go up high enough. But when you look at more regular loads, so not extreme situations or not peak situations, but your average situation, you see that the XGBoost model performed a lot better. It much closer follows the loads. And so that brings us a bit to how do you evaluate a forecast? What is a good model? Like by eye, you could say, I like this better or I like that better, but how do you quantify that? Well, for net congestion forecasting, of course, we're interested in peaks. We want to know when the grid is going to cross this threshold. We're not so interested in what happens when it's relatively quiet on the grid. So actually, we decided to go quite extreme on that front and really go for converting this regression problem into a classification problem. So what does it mean? We draw a line somewhere. In this case, it's about negative peaks. And we say, these are the moments when the load crosses this line when we're really interested in. And we just say these are every day, we say, is there a peak or not? So it's a peak day or a not peak day. And then we do the same for the forecast, the green line here, where we can say, was the peak forecasted that day or not? And then you get some missed peaks, some incorrectly predicted peaks. So sometimes the model forecasts a peak, but it just didn't happen. And sometimes you accurately correctly predict the peak. And then you can create these metrics that are maybe well known to data scientists, but not out there. So those are called recall and precision. So recall would be, what is the percentage of peaks that we saw coming, which is the main thing we're interested in as a grid operator. We want to have that percentage as high as possible. We want to see all peaks coming. So like as an example, how do you compute that here? How many peaks were there in the real data? 4. And how many of those did we forecast in this example? Well, those two we didn't, and those two we did, so it would be 50%. So in this case, recall would be 50%. That's not really good. We, of course, want to go to 100. And then for the precision, it's if we predict a peak, what is the chance that it actually occurs? So you can see here we predicted 4 peaks, 1, 2, 3, 4, but only 2 of them actually turn out to be real peaks. So in this case, it's also a 50% precision. So now we have some real metrics. We want to maximize recall. That's the most important thing for us as a grid operator. And precision is, of course, also important, but the main metric at the moment is recall. And if you compute those for, in this case, the linear and the XGBoost model, you see that, the linear model definitely wins in recall for us. It's really good at predicting those peak moments. So that's why what it's good at. And the XGBoost model is, well, you see it now in metrics. It's good at the RMAE, which is a metric just says how far is it on average from the realized load on every data point. And in precision, it's also quite good, but that's because it doesn't predict a lot of peaks. So if it does predict a peak, it's quite sure that it will actually happen, but it doesn't predict a peak so often. So which model is best? So it depends on the use case. So for congestion management purposes, actually the linear model is great for us. And the XGBoost model is actually great for some other forecasting purposes. And I also wanted to come back to this slide because we're also say that we also doing a lot of research into the deep learning side about how can we also make sure that we use the best of the whole training history that we have and the recent history. We have some promising results with that, but I'm not going to share those today, unfortunately. Maybe that's for next year because it's too recent. Don't have conclusive results on that at the moment, but we of course are also looking into that. But coming back to the quote, goal of forecasting is not to predict the future, but to tell you what you need to know. Well, for congestion forecasting, we need to know the peaks. We need to know when is the grid going to be over capacity. So we need a model that can accurately forecast that. So that's what we're going to use in our production system to run congestion forecasting with. And I want to say, so these models are available in openSTEF. So if you're also interested in applying that, so the same models that we deploy in production at Alliander are there in openSTEF for you to use. And if you're interested in using it, there is also a reference implementation. It contains these open source libraries on the right that you can quickly get started making forecasts for a couple of locations easily. And there's also a dashboard connected to it that you can see your forecast, so it's easy to get started. In 1 second, I'll be all right. I wanted to highlight the community. So Alliander, we use openSTEF, but we're not the only ones. We develop it together with RT International and RT and Viran, Sigholm, and Shell. We have community meetings every 4 weeks. So if you're interested in joining, then reach out. You can find openSTEF on the GitHub. There's a lot of example notebooks there that can get you started on making a forecast. All you need to do is collect that data, like the weather information and some other things, and then you can just plug it in, and it will make the forecast for you. Have a look at the LF Energy website or contact us at this Dutch address, which means short-term prognosis in short-term forecast in Dutch. Or find me after the presentation. And that's it. Do you have any questions? Yeah?
I have two, but it's general, but it's quite specific to forecasting. So I'm from Energy, also TSO. We have similar needs for forecasting load. And something that I noticed, you mentioned that brute force calculating is one way to do it, but then you need to know topology and everything. But one thing I think is valuable, especially as you said, so that the model can learn from past to know how to work in the future, is also to include the installed capacity to the time series. So you know the installed capacity in the past and in the future, let's say, that really helps the model to, even doing the zero-based models, to sort of find some correlations between the installation and output. And then a very detailed one is that what we have found is very useful is to also give the model not always previous day load, but also the previous day temperature. There is one day shift in the heating, and it really affects the performance. That's all.
Okay, thanks. So I'll quickly repeat. So the last thing you said is to include also the temperature from yesterday. That's a good predictor. That's good to know. We're going to try that one out. And the other one is to include installed capacity as a feature to the model. I think I can agree that I completely understand that it will help the forecasting accuracy, but then again, it would mean that you need to know that. So you need if you need to know that for all points in the grid, what the installed PV capacity on all houses are that aggregate to that point in the grid. So I can imagine it takes quite a bit of effort to calculate that or to get that information. Let's say, but if you have it, then it can be an interesting feature. Yeah. Thanks. Any other questions? Yeah?
Could I just confirm that you're doing the forecast directly on the network rather than doing a forecast for demand and then generation and then compute the network that way? And is that because for the telemetry data you can only see the network, you can't actually see the raw demand and the raw generation?
So the question is, do you forecast net load or consumption and generation separately? And yes, indeed, so you already answered it. We only see load on the grid, and it's a net load. It's a combination of everything that's happening. It's consumption, it's generation, it's all kinds of generation, it's all kinds of consumption. So that's why the features that are being inputted into the model are like, well, everything that could happen. So solar, wind, all these usage profiles of all the different types of consumers. And the model just figures out how do I combine all these features to get to this aggregated point on the grid. Is it solar driven? Is it wind driven? Is it usage consumption driven? Yeah. So, yeah.
But have you tested having a model for the consumption and a model for the generation differently, and then afterwards getting the net load, because the predictors for each one of them would be different?
Yeah, so currently all the predictors are in the same, because in the end we observe only a net load, so we don't have separate data sets for generation and consumption. What we do is first create a forecast for net load, and then we have a separate algorithm, which is also in openSTEF, to then separate the components. So what is the solar component, what is the wind component in this net forecast, which you can do after you have this trained model. Yeah? State space models? Yeah, not. Okay. Right. Right. So currently, so the question is, how do you update the model as we go along? And currently, what we do is we try to retrain the model every day, and only if it has a better performance than the previous model, we replace it in production. And also if it's older than a week. So if it gets older than a week, we definitely replace it to make sure. So that's our way, I think, of updating the model weights really often. But so. Yeah, maybe we should talk after. I'm interested in the other approach as well. Yeah.
So you mentioned that this installable capacity household are not always easily available, but actually we have an entire database about solar panels in the Netherlands, and this attribute about installable capacity is also calculated. So it might be interesting to look into.
Yeah. Thanks. So the comment is there are databases, there are data sources out there for knowing installed capacity. And yes, that's true. But then, of course, you still need to know the topology. So how is all of that connected to that point on the grid that you're interested in? So how do you need to aggregate all of that to get to the installed capacity that flows to that point in the grid? And then again, you need to inject a lot of knowledge into the model, which you could do. But our approach is just to learn from the weather information and to see, and you can actually kind of learn really well just from the radiance data to learn what is the relation between sun and load on the grid directly without knowing the installed capacity. Yeah. Yeah. Well then, I'd like to thank everybody and have a nice, I think there's one more session, or is this the last session? One more? One more, okay. So enjoy the last session and enjoy the rest of your time. Thanks.